Okay, I think we're live. Okay, I think we're live. Okay, cool. All right. Let's start, I guess. So, welcome to the Novcourse 2024 Advanced Editorial. I will not be streaming this on VC, so yeah. Okay. Anyways, welcome to Novcourse 2024 Advanced Editorial. I think I will first send the. I will send the link to. All right. I think we will start at 3:15. All right, it's 3:15, so let's start. So welcome to the Novcourse 2024 Advanced Editorial. So let's start. So question one is replanting potatoes. So this is a bridge statement. So you have a bag of, you can buy a bag of potato seeds of each type from 1 to n plus 1 for 1 cent. Then you can turn a bag of type C into K bags of types T1, T2 to Tk as long as the sum is equal to C. So find the minimum cost of buying potato seeds such that you possess a bag of potato seeds of each type from 1 to n. So first of all, subtask 1, n equals to 8. You can try all numbers from 1 to 9 since you can only buy that many bags. The answer is 6. Similarly, this subtask is for you to be able to find the pattern. So experiment with the problem. So you can always try all numbers from 1 to 89. But you would find that the answer is actually 77. So, full solution. So the observation that we have to make is that as long as we get a sum of 1 plus 2 plus all the way to n, we are done. We don't need to buy any more bags of potato seeds since we can just split those that we don't need into more useful bags, and eventually we will definitely get to 1 to n. But we also cannot afford to split bags of 1 to n, since that means that we have to form another bag of that type to fulfill the condition of us having at least one bag of types 1 to n. So what you realize is that you can actually buy a bag of type n plus 1, and this type n plus 1, you can split it to form all the bags of potato seeds of smaller types. So we greedily want to have the maximum amount. We want n plus 1 to split into the maximum amount of bags possible. So we will want to buy a potato seeds of types k to n plus 1, and we want to maximize k. So how do we do this? Well, for this solution to be valid, we have n plus 1 has to be greater or equal to 1 plus 2 until k minus 1. And this is a primary school formula where where 1 plus 2 plus 3 all the way to k minus 1 will be equal to k minus 1 times k minus 1 plus 1, which is k, over 2. So we binary search for the largest possible k. Yay! So question 2 is potato sequence. This is an overlap with elementary final, so I will not be going through it separately. You can go check on Novcourse 2024 elementary channel for the solution. Similarly for question 3, this is an overlapped. So question 4, delivering potatoes. I was too lazy to abridge the statement, so just go read the statement. It's pretty short anyways. So for k equals to 1, since Bribrit can only carry a potato at a time, well, the answer is just the distance between Bribrit's house and coordinates of house k. Remember to times 2 because he needs to go there and come back to replenish the potatoes. However, do note that this is probably inaccurate because for house n you can just go to house n and you don't need to come back. But I think, overall it should be correct. For n less than or equal to 8, you can use next permutation, which is O n factorial. And you brute force through all the possible permutations of serving the houses to figure out which order of visiting the houses is the most optimal. Now, for the other subtasks, I will just skip the solution because of time constraints. But for the purposes of this explanation, we define house I as the house of customer I. So to save. Okay. Then so for the so for each I from 1 to n, there are 2 possible paths of giving a potato to customer I before giving one to customer I plus 1. So you can directly travel from house I to house I plus 1, or you can go back to Bribrit's house for house I and replenish your potatoes before heading towards house I plus 1. So let T1, T2, or T2L be the sequence of moves where we choose to go back to Bribrit's house to replenish potatoes. The constraint is that since Bribrit can only hold as many, at most k potatoes, hence Tj plus 1 minus Tj has to be less than or equal to k, since we can only hold that many potatoes at that time. Let di be the distance we save by going directly to house I instead of going back to the Bribrit's house. And we can break the problem down to, you are given a sequence of integers from d1 to dn minus 1. You have to choose some number of terms such that no 2 terms are distant by more than k. And hence, you want to find the minimum sum of the
An earthquake of maximum measured intensity of 1 occurred.
Don't mind that announcement. So continue. Let's continue. So dpi is equals to the minimum sum of the chosen terms of the I when choosing the ith term fulfilling the conditions that we stated here, which is no 2 terms are distant by more than k. So hence dpi is the minimum of dpi minus 1 plus and dpi minus k plus 1 all the way to dpi minus 1 plus di. So how do we compute this thing? Your first thought might be to loop through, but the problem is that is very time consuming. So I think that's the O n squared solution, where n less than or equal to 1000. So what can we do? We can maintain a sliding deck. This is a classic technique from lecture 1. So what happens is that we maintain a deck to keep track of the smallest dp from I minus k to I minus 1. Hence, now we can efficiently compute dpi in O1 times, since what happens is that the front of the deck would be just this value. So now your final complexity will be On, since you'll be computing dp for each number, and hence your final answer will be dp of n, which is, yay, we have solved the problem. Alright, last question. Transporting potatoes. This was written by Brian Xiao and Simon Gu. So a bridge statement, there are n plus 1 times m plus 1 houses in the grid and n times m roads connecting them bidirectionally. Each road either connects ij to I plus 1 j plus 1 or ij to I plus 1 j minus 1, so diagonally. It causes money to flip the road from one to another. So starting from at house xy, for each house, find the minimum amount of money needed to get to that house. So if it's impossible to do so, just print -1. So for k equals to 0, this means that the cost of ij is equal to 0, and hence we just have to determine which houses are reachable from xy. The answer to a house is 0 if that house is reachable from xy, and -1 otherwise. We claim that ij is reachable to xy if and only if the parities of I plus j and x plus y are the same. So we realize that to move from xy to another house nx, ny, the value of nx plus ny is either x plus y minus 2, or x plus y plus 2, showing that the parities of nx plus ny and x plus y are the same. So the parity of x plus y is invariant. Okay, so it's basically O and M. So for n equals to 1, what happens is that notice in this subtask, there's exactly one path between xy and any reachable house, and this path looks like a zigzag pattern. So we can now use a simple DP to find the answer for all reachable houses. So if a single source house and we want to find the distance to all other houses, you should be reminded of Dijkstra. So consider a graph with n plus 1 times n plus 1 nodes and one node for each house. If a pipe of type that going down to the right is with cos C connects ij to I plus 1 j plus 1, we connect the nodes corresponding to ij and ij plus 1 j plus 1 with an undirected edge of weight 0. We also connect the nodes of ij plus 1 and I plus 1 j with an undirected edge of weight C. So now we just now similar edges are connected if the pipe is of type basically the other way. Wait, oh my bad. So yeah, so we can run Dijkstra from the node corresponding to xy, and the distance of the nodes is exactly the answer to the house. The proof is left as an exercise to read out. Yeah, so cool. So subtask 5. We observe two optimizations. So we make optimization 1 is that we can make use of the incredibly small bound of k and use Dio's algorithm, which gives us k and m, O of k and m. And in terms of memory optimizations, we notice that there are 4 and m which is less than or equal to 2 times 10 to the power of 7. So we can remove the adjacency list to store the edges and calculate them only when we need to. This is very implementation heavy, as there are many edge cases and messy bit calculations, but it does reduce the memory usage by quite a bit. So it was originally intended for both optimizations to AC, but Dijkstra from subtask 3 and 4 had a higher time complexity than the intended solution. It was actually marginally faster in practice. So as such, solutions with only optimization 2 were also allowed to pass. So intended was 2.31 seconds, scam was 2.26 seconds. So this is, So I hope you did enjoy the contest and that you learned something from Novcourse as well. And that's it. Thank you for joining Novcourse. Yay. This is a